Okay, good afternoon. Today we will discuss the acceleration. You remember from the beginning of these lessons we discussed what is machine, what is mechanism, and then the structure of the mechanism and mechanism design of the mechanism, and then freedom and joint, all those things. Then finally we discussed, we finished the after design of the mechanism, synthesis of the mechanism, we discussed the acceleration, velocity. Now we will discuss the acceleration. That means acceleration, you know, we are talking about the 4-bar mechanism, and 4-bar mechanism, let's say, general 4-bar mechanism. So we learned how can we design a mechanism for a given expectations. That means we define the geometric dimension of the mechanism, and then we after that we said, okay, after dimension we have to able to calculate also kinematic velocity and the acceleration. And of course, in the following lessons, the topics will be dynamic. That means the static forces, dynamic forces, and so on. And today we are going to discuss the acceleration. So acceleration for the link 1. So link, let's say this is the quick, this is doesn't move. So fixed, grounded. So this is the acceleration link 2, 3, and 4. So any point on 2 or 3 or 4 is important for us, and we should be able to calculate the velocity and the acceleration after defining the geometry, that means synthesis. So the measure of the amount that parts of a machine are speeding up or slowing down. So each machine we use in industry or industrial environment, so always there is a speed up and speed down. That means the speed is changing. So since speed is changing, that means we face to acceleration. So if the speed is changing with time, for us, we learned in the dynamic that speed is changing. So delta is d over delta t is the acceleration. So, and we have it. We have it in the machine. So if machines start to work, the speed starts from 0 and come to the nominal value. That means speed is changing. And if you stop the machine, also speed is changing from nominal speed to the down to 0. And since the speed is changing with time, we have acceleration. So what's the acceleration? Actually, we learned already dynamic. So, and we said also we use lots of different mechanisms in the machines. So then, if we design a machine, we face these type of problems that we have to calculate according, depending on the mechanism which we use, which we apply in the machine. We should be able to calculate the speed and acceleration, because speed and acceleration is important for a machine. So important because the force is required to produce acceleration. So we know also from dynamics that F is equal, force is related, mass and acceleration. So force and mass are in a certain relation. We call it second Newton's law. And let's start step by step and talk about the acceleration. First, linear acceleration. You know, from the other, so the acceleration is equal dv over dt, differential part of the speed, velocity over the time, changing with this. This speed is changing within this time, or we can write it depending on the position vector. So, regarding considering the position vector, the second time derivative. So the A is equal d2r over dt dt square as the position vector. So also we know these equations from the kinematic that for constant acceleration we write speed changing is the acceleration constant. That means the acceleration is not changing. So then we write delta V is the final and the initial. It's the difference between final and initial speed and A time delta T. And also we know these equations from dynamics that the difference regarding the position is equal 1 over 2 times A times dt square plus the initial dt. So if you want to calculate the position of the motion of any point participating to the motion, or we can write the final square is equal to the initial square plus 2a delta r or delta s. We wrote in dynamics. You know how can they derive these equations? So, okay. Let's have a simple example regarding the acceleration. Let's think that a linear actuator is extending to hydraulic actuator extending at a rate of 70 millimeter per second. That means this is the speed. Extending, start to extend. So once power means per second, then there is no power anymore supporting the cylinder, so it goes a little bit forwards, stop. That means the speed arrives 0 within the time of 0.7 seconds. So determine the acceleration and additional displacement of the actuator and additional displacement. So how can we calculate it? The speed started from 70. This is the, let's say, the initial speed. The initial is equal 70 millimeter per second. Millimeter per second. Okay. And the final must be 0. Isn't it? Must be 0. So, and the time is 0.7 seconds. Delta t is equal to 0.7 seconds. So the acceleration, you know, the acceleration is equal A is equal delta V over delta T, and this is and V F minus V initial over delta T. So this is minus, so the final is 0, initial is 70, so this is equal, A is equal minus 70 millimeter per second, and time is 0.7 second. And this is equal, sorry? 100, huh?
100 mi?
Evet.
Eksi 100.
100, evet. Minus 100 millimeter per second square. Why minus? Stop. Yes, stopping, huh? Not the acceleration. The acceleration, right. So that's the reason. So this is the acceleration. And determine the acceleration, okay, and the additional displacement of the actuator's end. Additional displacement. So additional displacement, that we don't know the initial displacement. Therefore, from initial displacement to the final displacement, that means the stopping period. So it's the question here. So for that, we can use the equations here. So delta R is equal, we can write here, delta R is equal, right? So we cannot, so with this equation, maybe you have to use these equations. So we have the final speed, we have the initial speed, we have the acceleration. So with these equations we can solve it. Because
Hocam bizden sadece şeyi istemiyor mu? Yavaşlarken aldığı yolu.
aynen onu istiyor.
Yani en başta sabit hızla giderken ki aldığı yolu istemiyor.
İstemiyor, evet.
O yüzden sadece 1/2 AT kareden kullanmamız gerekmiyor mu?
1/2 AT kare orada da kullanabilirsiniz.
Yani o alttakini kullanmak yerine.
Burası 0. Bakalım aynı sonucu verecek mi? Biraz bir silgi alayım.
Getireyim hocam.
Evet, teşekkür ederim. Let's use these equations here. Bf square is equal Vi square initial speed square plus 2a delta r, and we are looking for delta r. So Vf is equal final speed is 0, 0 is equal, the initial is how much? The initial 17. 17, let's use this one, okay. $17 square plus 2 times 100 times delta R. So delta R is equal minus 70 square over, is also minus 10 plus 200. 2 times 100 2 times 100. So then over 200, 2 times 200, okay.
24,5 galiba hocam.
So and then
Galiba 24,5 ediyor.
so 24. Doğru. Öbürü de aynı sonucunu veriyor.
Onun denemedim.
Okay. 24.5 millimeters. So that's so. You know how we write these equations. It is very, and we derive from, we learn in kinematic. There is.
These are normal Newton motions, right? Newton's motion.
You know that, huh? Displacement over time. Oh, you know, and A is equal dE dt. Huh? We know also that. And using these equations, and here from here dt is equal dV over A. dV over A, right? And here V is equal ds, here we can write dV over A, and this is equal ds times A dV, and that means ds A is equal V dV, and this is ds delta S. So then apply the integral. A is constant, huh? So A times S1 plus S, or S2 plus S1, and here 1 over 2 D square, isn't it? Sorry, 1 over 2 D square, but the final minus square minus B initial square. So then this is delta S here, the difference, A times delta S, S is equal here 1 over 2 so now let's take the 2 here. So then the final square minus the initial square. So, and the final square, I think this is the final square is equal, the final square is equal the initial square plus 2a delta S or delta R. Huh? This is the equation. So it comes from here. It is very easy. You can keep it in your memory. I mean, you shouldn't memorize all of them, but you should know the way how you can count. We have in kinematic, we have two important equations. It comes from the definition: velocity and acceleration, and S is the position vector or position. So then, using these two equations, we create another one, and this is these equations here, and use it there. Huh? This one. Okay.
Hocam biz böyle kağıt tekrardan da direkt geliyormuş aynısı.
Aynı sonuç
Aynı
çıkıyor.
sayfa geldi.
Aynı sonuç, evet. Okay. Yani, so if we use from the simple way, S or delta S is equal A T square. It comes, from the again from the equations. We can also calculate here the displacement. Not only that, we can calculate displacement. Displacement is equal, displacement delta or the S is equal S initial plus V0, V initial times T plus 1 over 2 A T square. This is the equations. So this is another equations. If you have initial and final and all those things, that means if you want to calculate the whole length, but we don't know the initial parts of the length, and therefore we calculate only after cutting the power how long cylinders how much change its displacement. Okay, so then this was a simple example, but now we are going into the direction of the mechanism. So this is now the mechanism, like you see here. So we have 4-bar mechanism, and we are talking now about this part here, the driver. And this type of mechanism, you see, this is driving part, driver. This link 2 is driver, and the other couple, and the rocker is the driven part, and driver, if you consider driver, and the acceleration of the point, any point, let's say the B here, somewhere. So we learned already in kinematic that the acceleration generally consists in two parts: normal component and the tangential component of the acceleration. And we said the acceleration is caused by a change in velocity. So if there is no change within time regarding the velocity, there is no acceleration. So magnitude-wise, we can say tangential acceleration and the normal acceleration. So tangential acceleration is the magnitude-wise important. Normal acceleration is the direction. So we learned also tangential components of the acceleration, dv over dt. So dv over dt, what means that? Tangential component at is equal the linear speed over time. And if you write d over dt, for example, here, instead of v, r omega, if it is the rotation, not the linear, this is linear acceleration of a point. Okay, linear, we will come to that. So don't mix it. And we learned also that the normal component is v square over r, or the radius here. That means the length of the link. So then let's continue as an example. Here, small example. At the instant shown, like in the picture you see, point P is moving at 750 millimeter per second. Point which point? Point P. So this point, huh? No. Shown power is so at the instant shown, the power is suddenly cut. The link will slow down, then stop in 3 seconds. Determine the acceleration of the point P. So we can calculate it. So determine the acceleration to point P. So to point P, the acceleration. So acceleration point P. So we know the acceleration consists of two parts. Tangential is equal dv dt, and the normal an is equal v square over r. You know. So the instant shown, point P is moved. That means the initial speed. So V initial is equal 750 millimeter per second, and at the instant shown, the power cut is suddenly cut. The link will slow down, and so slow down. That means the final is equal 0, and the time interval delta t is equal 3 seconds, isn't it? So, here delta v is equal so delta v is equal 750 millimeter per second, and time is delta t is equal 3 seconds. So here the acceleration is 750 over 3 is equal so a moment. Millimeter per second square. Is it correct? Okay, so this is the tangential acceleration.
250.
Sorry?
250.
250. Bir 15, 3, 5. Right. So, 250 millimeter per second square. So, what is the normal acceleration? The an is equal v square over r, and so on. V is how much? 750 over 250 is equal
750'nin karesi olacak hocam.
kare, okay. Square.
2.25.
Here, what is it?
2.25.
2.25.
25.
Millimeter per second square. So this is the normal component. And the total acceleration is equal, A is equal A t square plus A n square, but they are perpendicular to each other. So then at the end we have here the 150 square plus, I'm sure that this must be more, I think.
225 hocam galiba. 225 dedim.
No, 750 square
Yes, 750.
square
750.
divided by 250.
Why are we using this equation? It's
2.25.
not a tangential path, it's a straight path.
Hmm?
Right? We only use this equation when it's a curve, right? But this is a straight linear path.
But this is, I mean, it has tangential and normal component.
But it's moving in a straight line.
Hmm?
Does it have a curved path?
It moves like this.
Okay, so it's like a
Circle like this. Huh? So it's the point P. And has the speed. So it is not given actually direction. Stop means, yeah, from this speed, okay, it's correct. From this speed goes down. Let's say at this instant, this position here shown has 2500 millimeter, 750 millimeter per second speed, and the cut speed is cut, power is cut, and then it has to stop. Okay, then stop in 3 seconds. Determine the acceleration at the points. Yes. And this is the value of the acceleration in total. 2.25 square. You can calculate also here the angular velocity. Check angular velocity. So angular velocity is also can be calculated because this angle it's stop down, so goes in that direction. So there's 35 degrees in how much? In 3 seconds. So in 3 seconds, yes. Also could be calculated. Okay, so then let's continue. Rotational acceleration. If things are rotating like this, so the rotational acceleration, rotational acceleration, if it rotates like this, let's say counterclockwise, this is theta, and it moves in that direction. So the angular speed is omega is equal delta theta over delta t, and alpha acceleration is d omega dt, or second time derivative of the position angular position dt squared. So, and also we can, using these two equations, I mean here, we can create, like we did it for the linear motion, omega final is equal omega initial final square omega square plus 2 alpha delta theta. like the equations we created before. Huh? So like this one, we said V final square is equal V initial square plus A two times A delta S or delta R. The same. This is linear displacement. This is angular displacement. Okay. Start from the zero. So it starts from the zero. This is the time axis, and this is, let's say, the RPM. RPM from zero start, come to this level, and this level is, you may take grinding here. This is the diameter is turned on, speed up 300. So this is 300 RPM and 1 point, and time is for that 1.2 seconds. So 1.2 seconds. Determine the acceleration of the wheel. So how can we calculate it? Acceleration is equal, the acceleration, the omega dt, the omega dt angular acceleration is equal. So we have to calculate the omega first. How can we calculate the omega? So omega is equal to Pn. And that means the omega change from 0 to this value. This is the omega. Omega initial is 0, and this is the omega final. So this is, we calculate omega final. Omega initial is equal 0. And here, this is equal to 2 pi and 300 over 60, because RPM, minutes, we change into seconds. So, and then here we have, okay, 0, 0, 5 here, 5, and this is nearly, let's take it 3, 6, 30, huh? Around 30 radian per second. So, and alpha is equal delta omega over dt, and it's equal here 30 because it starts from 0 and arrive at 30. In between is the difference of the regarding angular velocity is 30. So alpha is equal 312 and is equal per second square. Is correct? Huh? No. Okay. So that's linear angular acceleration. Linear angular acceleration. So we come to the driver of the mechanism. The crank we call crank. Crank is driver, like a crankshaft in car. Driver. So let's say we connect the electric motor. If we use the electric motor to the crank, and we put into the motion, or we connect to another power unit so that it starts to turn, like combustion engine and so on. And if it is the driver, so we should know about the driver. What should we know? We should know the angular velocity, and if there's an angular acceleration, we should also know that, the angular acceleration. So we know also that the acceleration in the other direction, opposite direction, not in the same direction. So like you think, for example, if you how to say, if you want to travel with a dolmuş universe, it's very famous in our country. Where are you from? From Syria. Do you also dolmuş culture in your country? Dolmuş? Huh?
Maybe yes.
In Egypt?
Mm-hmm.
Yes?
Yep.
So besides of the, how do you say, public, how to say that, public? Transportation, right. Public transportation. Besides of public transportation, we have our famous dolmuş culture. And if you travel to dolmuş, if you say that, if dolmuş starts to move at the beginning from zero, so because they drive very fast, and let's say, you tend to move in that direction, not if start to move. So if he's trying to stop, so you move in that direction. So that means the opposite, compared to the direction of the speed. Yes, right. Third law. And this is not the mass, this is the acceleration, mass time acceleration. So mass doesn't have any direction. Mass is mass and the properties of the material. So, and if the velocity is in positive direction, acceleration is negative direction. So that's the reason why it's shown here. This is the angular velocity and angular acceleration. That direction. And we said also the normal point on this driver, let's say the point B, has based on that, on the motion, that means the acceleration, and the motion with acceleration has also acceleration, and the acceleration can be divided into parts perpendicular to each other, tangential and normal components. And then we said also tangential is equal dV over dt, and if we write in state of V, r omega, we can write, V is equal r omega for the circular motion. And then we achieve tangential components are alpha. So that means we can easily calculate that. AT for the point B, and this is R times alpha. So, and the normal component is equal, AN is equal V square over R, so that. Knowing that, we can solve this problem maybe. Huh? So the link a shown is rotating clockwise at 300 RPM. Clockwise, that means in that direction, clockwise. And slowing down at a rate of 600 radian per second square. That is the acceleration, angular acceleration. So determine the acceleration of the point A and B. So determine the acceleration of the point A and B. Or maybe we use, let's say, can see, I don't know. Maybe we use here, let's use this part of the table, board. Okay. So what is given? 300 RPM clockwise. Okay. N is equal to 100 RPM clockwise. Okay. And slow down with angular acceleration. Alpha is equal 600 radian per second square. Determine the acceleration of the point A and B. So first the A, let's say the acceleration, requested acceleration points A and B. So first the A, and we know the acceleration, A tangent and A normal, so we have to calculate. And A tangent is equal, what? R alpha, we learned already, we shouldn't forget it. Here, AT is equal R alpha. From here, so R alpha, alpha is given, R is given, isn't it?
Yes.
So and then AN is B square over R. Also clear, huh?
So V square times R.
So V square, right, V square over R, this is the AN. So let's calculate the omega first. Huh? We need omega. So omega angular speed is equal 300 let's say 2 pi n over 60 to, let's say 300 over 60.
No, but we have omega, right?
Huh?
600 radians. We have omega already. Right?
Yeah, but
We have omega already 600.
no, this is not omega. This is alpha.
Acceleration.
Angular acceleration. Radian per second square. This is angular. Slow down, huh? So the omega is equal here. Okay, 5, and this is 30. 30 radian per second square. So, and we can calculate the V also. V is equal R omega. R is known, V is known. So we can easily calculate it. Huh? I will not calculate the end. Any question?
Yes.
So you all are very successful in the midterm exam, and now you are
Hocam,
Why?
it's written that alpha is omega square times r.
Hmm?
Alpha
Alpha?
and m. It's omega square times r.
AM you mean,
Yes,
is equal.
omega square times r. Right?
Okay, yes, this is all same, but let's say if we write instead of D, we can write R omega, square, omega square
Okay.
over R. So then it is equal R omega square. Correct. No problem. So, rest you can solve. There are different methods to calculate the acceleration for the mechanism, in case of fluid mechanism, for the mechanism. One of them is the analytical way, the other one is the graphical way, and the other one is the algebraic. So the algebraic here in the book, and I will not lose time for that. Those are the formulas. Time derivative of the second time derivative of the position vector. But I will discuss the topic, the graphical way. Because yesterday also we mentioned shortly that if you write a program using the equations and try to calculate the acceleration or the velocity or any other geometric dimensions or thematic parameters, so you shouldn't trust the result coming from the calculation, coming from the computer. You have to check it, whether it's correct or not. And to check it, regarding the coordinates, you have to use the graphical way. You have to draw and check it whether it's correct. I did it in the past. So I write a big program for the kinematic and kinetic, kinetic and kinestotic. There are, it was many years ago, and at that time we didn't have such a sophisticated software. We had to write, we had to use, I used the Fortran 77, and it was the one language at that time to program, let's say, to solve the scientific problems by programming. And lots of equations, at the end we get some results, and you don't know it's correct or not. Maybe you did a mistake with the calculation, or you write it in formula or the formula by itself, because some of them you create. You don't know. You have, at the beginning you will be surprised, maybe the result will be not. So then you have to check, maybe 0 divided and something like that, and you have to correct the equations again, and then you get the results, some let's say values, some number, but you don't know it's correct or not. And you have to check. You have to check it by calculating the same parameters using graphical methodology.
Hocam, what do you think about MATLAB?
MATLAB, I mean, my MATLAB is okay. MATLAB doesn't make mistakes. But you put the equations in. This is what I mean. MATLAB, I mean, MATLAB is okay, but MATLAB cannot calculate by itself. It's saying that you have to put the equations. When you put the equations, you can make mistake by putting the equations. Or the equations could be wrong, or could include some mistakes. We don't know that. Check to convert by graphical methods. So, the acceleration analysis, relative acceleration method. We will use the relative acceleration method, and that means we have here the Krankowka mechanism. 2 points on a rigid body can only have a relative tangential acceleration perpendicular to the line that connect them. We learned in the chapter of velocity. So, therefore, the relative normal acceleration is along the line that connects them. That means the normal component of the acceleration must be on this line. If we talk about the relative normal acceleration or relative normal component of the relative acceleration of the point B. Okay, that means that so you may remember the right for the relative motion is that VB is equal VA plus VBA, isn't it? You remember these equations, relative motion. And that means here, like this. This is the A, and this is here the B, and this is ground here. Huh? So, if we know normally we know the velocity of the point B, A, sorry, because the driver must be given. Okay? Driver must be given, so we know that. And using the relative velocity method or relative velocity method, we can calculate the B. VB is equal VA plus B about the point A. Motion about the point A. B, motion of the point B about the A. So, so then, same for the acceleration. You see here, this is, let's say, the I is any link of the mechanism. So we know that each acceleration has normal, in general, two components, normal and tangential components. So we can write here, actually, same way, AN, so A acceleration B is equal acceleration A plus acceleration BA. So, then instead of A, we can write acceleration B tangential plus acceleration B normal is equal, like this. So here, this is the equations. The link I, normal component, link I, tangential components equal link N, link G, normal, link G, tangential components, and the relative acceleration between them. That means the G about the I. Must be G about, okay, this is G about the I, okay. So the positions on translating links have no normal acceleration. So points on translating links, it's pure translation, there is no normal component of the acceleration. If the endpoint, let's say, undergoes a linear motion, so there is no normal component. Points on links that rotate at constant speed have no tangential acceleration. If it is constant, time derivative, first time derivative of the speed must be 0 because it's constant. So, okay. This is not correct according to my observation. I have to change it. It must be AI is equal G plus G about I. Let me say the difference. So I have to correct it. It is not correct. G over I. Right. So this is the correct. I is equal G plus G relative to I. Okay, here the same. I G. Okay, here against G about I. And here also G about I. So it comes from here. Huh? So if you write, normally we know the A, because A is the point on the crank. And the motion of the crank must be known. This is driver. So since we know the motion of the A, so we have to calculate the, let's say, the velocity of the B. B is equal, B relative velocity calculations. VB is equal, VA, we know the A, and relative B about the A. That means the B is turning about the point A. So this is the main way of thinking. Here is the I plus G and G plus G relative to I. And the same. Relative G relative to the I. Okay, let's have an sorry, a moment. Okay, we use an graphical way to calculate the acceleration and our famous crank slider mechanism. First, we'll talk about the crank slider mechanism. You know, the crank slider mechanism is the mechanism we use in the car, in the internal combustion engine. Very famous mechanism. We use in press, for example. Many applications. So therefore, it is the important mechanism in mechanical engineering. The crank of a slider crank mechanism rotates clockwise at a constant speed of 300 RPM. Crank must be given because this is the, you have to start from a point which is known, and this is the crank, motion of the crank. So the crank is 150 millimeters length and dimensions given, and the connecting rod is 600 millimeters. This is the coupler. And determine first linear velocity and acceleration of the midpoint of the connecting rod. That means midpoint, okay? And second, angular velocity and angular acceleration of the connecting rod at a crank angle of 45 degrees from inner the center position. So dimensions are given, and the initial position of the mechanisms are given. So we have to calculate the velocity of the midpoint of the connecting rod. So it's one linear velocity and the acceleration of the midpoint, okay? And second, we have to calculate the angular velocity and the angular acceleration of the connecting rod at a crank angle and so on. So can we do that? using the graphical way and also analytical way handled by the calculator. So this is the mechanism here. And we have to use a scale. So we cannot draw one-to-one. Scale means you cannot draw a given mechanism or given any mechanism with the same, let's say, dimensions on the paper, because paper is small and mechanism can be huge. So therefore, we use scale. 1 to 5 means we have to in the picture drawings, if you measure 1 millimeter, that means 5 millimeter in reality. So, okay, so this is the crank slider mechanism inline. So could be offline, and we know the motion characteristic of the crank. The position is given 45 degrees, length is given, and speed is also given, because the RPM is given. So let's see that. We know the RPM is about 300 RPM, OA. Crank is going with 300 RPM. At 300 RPM means 31.42 radian per second. Omega. So then we can calculate the velocity of A, linear velocity. Linear velocity is, you know, the distance times omega. So here, and this is at 4.71 meter per second. So then we have to calculate the velocity of the point B and the relative velocity A relative to B. And we learned in our previous lessons in chapter velocity. So how can you calculate it or define it using the graphical way? We use also a scale here, and we said 1 centimeter is 1 meter per second for the speed, velocity. So we know magnitude and the direction of the VA. So VA is known as magnitude and as VA is known as, let's clean the, okay. You can make such a table, like this is the link to point A and point B, and you can say B relative to A, velocity. And the velocity, for that, we know the, let's say, the magnitude, and the direction. And then if we know the magnitude and direction, we know the speed. So that means the speed, velocity is known. So let's come to A. A, we know the magnitude, isn't it? We can calculate. That means 7. Magnitude is also known, and the direction is also known, because it must be perpendicular to that line. Tangential speed or linear speed. So this is also known. Okay. Let's come to the B. B. What is known? We know the direction. We know the direction because, you know, it can move only in horizontal direction. So direction is known. We know the directions. Okay, but we don't know the magnitude. And we use the, to calculate velocity of B, we use the relative speed equations. What about the BA, B relative to A? Or let's say, oh, this is not correct now. I have to change it here. B, okay, this, okay, B, and A to B. Okay, let's A to B. A over to B, right? A over to B, correct. A over to B, right? It is B. So, what we know about the A relative to B, speed, I mean speed. What we know? Direction. And the direction must be perpendicular to the AB, isn't it? So must also, that means the motion of the point A relative to B. So, like a circle, huh? So, and must be perpendicular to AB. So I know the direction. I know not the magnitude. So therefore, I mark the point here, and I draw the A, BA. This is BA. I know the magnitude, I know the directions. And from the end of the A, the BA, I draw a line perpendicular to AB because it's the relative motion. So perpendicular to the line AB, and then the second line from the O to the parallel to the direction of the velocity B. This is horizontal, and the crossing point is here. That means this is my BB, and this is B relative to A relative to B, like this. And our vector calculations, so BB is equal BA plus BBA. So like this here. BB is equal BA plus BAB. Okay, so, and then he's saying that what is the speed in the middle of the coupler? So since it is in the middle, so using the geometric properties, it must be also in the middle here, relative. So then, or let's say that this is the angle-wise must be the same thing. Here we can draw, and this is the we know the direction. We know the point here must be the same. Because this is the middle. So then we know also the linear velocity of the point, the middle point of the coupler. Okay, this is the speed, velocity. But we have to calculate the acceleration. This is our main target, the acceleration. But please be sensitive about that. Without acceleration, without the velocity, the acceleration is not possible sometimes. So first, the acceleration, velocity, and then acceleration. Huh?
Sometimes or always.
Yes, yes, you're right. Yes, you may remember from here. I say these are our I say the S is equal. Let's say the function of time let's say the displacement, and we calculate the velocity is equal ds dt, and acceleration is equal dv dt. Yeah? If we find the v, and we can calculate the acceleration also. So then let's continue. We make a table like this, like I did it here. And for each member 1, this is the member 1, member 2, and member 3. So member 1 is OA, member 2 is AB, 3 is B. Slider. So we are looking. So we are interested to calculate the acceleration, but we know each acceleration or acceleration for each point consists of two components, normal components and tangential components. So therefore, I'm right here. This is the tangential part. This is the centrifugal normal part. Tangential, normal, tangential, normal, tangential, normal. But I know that for the beginning. So I know for the link one, I know the tangential speed is 0 because speed is constant. If velocity is constant, dv dt is equal to 0. That's the reason. So, and we calculate, as we see, the VA, we have to we calculated already. V is 4.771 meter per second. Since it is constant, and time derivative of constant is 0. Therefore, tangential component is 0. And the normal component, so normal component is equal what? V squared over length, or OA. So we can calculate. This is 148 meter per second square. Good. So then we know that. And let's come to the link 2, that's the coupler. And we know the direction only for the normal component, isn't it? The direction, you know. This is that must be along the AB, normal component. But we don't know the magnitude regarding the time. I corrected. Talking about the tangential components AB must be perpendicular to that, to AB, tangential components, like this, perpendicular. And therefore, we know the direction. And normal component, how can we calculate normal component? We can calculate normal components. So in that way, VB square over AB. We know VBA, we have to, this is the VBA, we have to calculate. We calculate that VBA relative. And since we know the VBA, so over AB, we can calculate the value of the magnitude of the normal component. We know also the direction of the normal component. Normal component must go also in that direction. That means we know the normal component, direction and magnitude regarding AB, and we know the direction of the tangential components. So there is magnitude unknown. Let's come to the slider. And in case of slider, so we know the direction, and we know also that slider doesn't have normal component. The normal component is 0, y 0. It's not rotating. It undergoes the linear motion. That's the reason. So we have here two unknowns. But unknowns means we know the direction, but we don't know the magnitude. So then we have to draw now using the scale. So we can draw first of all the acceleration of normal component of the So the AD is equal of and ABT tangential components is equal and ABA and so on. We make the calculations and then we can write this is the normal component of the A. And is there a tangential component? No, tangential component is 0. You know that. It's only normal component. In this scale, we can and component of the AB, we know because we know the magnitude of the AB, we know the magnitude, the normal component, and also the direction. So it must be direction, normal must be parallel to that line. And we calculate also the magnitude here. And so then we can draw a line from end of this point perpendicular to that line, because we are interested to find the tangential components. We know the direction, we don't know the magnitude. Tangential component of VAB. And then from this point here, we can draw, from this point, we can draw a parallel to the horizontal line because we know the acceleration of the point B had no normal components on the tangential components, linear motion, therefore we draw the line, this line, and cross here somewhere. And this is the system as a two line. I mean, this line and this line crossing there. And this point is important for us because this point shows us this is the acceleration, total acceleration of the point B. And this is the tangential components of the AB here, tangential components, AB. In the sentence or top you know that A tangential is equal dV over dt. Since B is constant, this is equal to 0, and a n normal component is equal V square over R, or R over R square, the same. So then we know the magnitude and direction of the acceleration of the point A, that means OA. If we come to the AB, we know the magnitude and direction of the normal components, like this here. Magnitude and direction, we know because direction must be in line with AB of the normal components. And we know also the direction of the tangential component must be perpendicular to AB, tangential component. So, and then let's come to the two sliders. A slider, we have here the slider. Okay, we know the direction, but we don't know the magnitude. We will achieve that by driving. And also here, achieve by driving. Horizontal component here, so. And also the AB tangential component will achieve by driving. So if we have only two lines missing and two magnitudes missing, so you can imagine that if you drag the polygon, I mean vector polygon, for the acceleration, somewhere they will cut each other. So then we will find the point where we can by measuring find the magnitude of the various unknowns. Okay, this is the graph here and the vector polygon regarding the acceleration. And I said we know the acceleration of the point A. This consists of only normal components, tangential is 0 because of tangential speed is constant. And then we know the relative, acceleration A relative to B, the normal component, because must be along this line, on this line. I can calculate the magnitude like this here. I know the VBA, I have already calculated, and I know the distance also. And then I know the direction and distance, so I mark it. So then I draw a line at the end because I know this is normal component, it must be tangential components. So perpendicular to that and perpendicular to this line here. And then I know the direction of the direction of the tangential speed of the point B, and this must be parallel to that line, to horizontal real line. And I draw a line from here, and they cross each other at the point B prime. And then, so I can measuring from this graph and using the scale, I can calculate the values of unknowns. That means here, 140, and this is also here. It's not written, but it's somewhere here maybe. Let's next. Okay, the next one. Is it given somewhere? Okay. ABA, ABG, BAD, okay. No, okay, let's see the next section here. You see, it's, the mathematical and geometry. Huh? So there is a homework for you. You have to do that. Yes, this is homework for you. You have to really drive it at home, huh? You have to really work on that. So, I think this is enough for today, huh? Next week, our last lessons, I will discuss with you the and then the time maybe a little bit about the count mechanism. And in the content of these lessons, there is also a mechanism content-wise included the belt mechanism, chain mechanism, and gear mechanism, and screw mechanism, but all of them we discuss in machine design too, and therefore there is no need to discuss here. And this also shown that is, I mean, very simple. But we discussed it quite detailed in machine design too, therefore there is no need. But count mechanism and so the important for you can be also the static force analysis and dynamic force analysis. And for the mechanism, the crank slider or crank rotor mechanism. But if you anyone make radiation physics later in that field, machine design, maybe he or she can work on that. And I have to. So next year we will start. So consider that I shows. So regarding the final thesis or graduation thesis, I am thinking in that direction. If you are interested, so the area must be industrial automation, machines are production or line, product or machines or part of the machines, targets to improve the functionality, to improve the performance, cycle time, for example, or improve the quality, or improve the maintainability, improve the safety of the machines, or reduce the cost, and etc. Could be different. And you have to make a review on this on the subject you want to work in this field in industrial automation. Maybe we use maybe sensors, and you are having also the lessons principle of mechatronics. Yeah. So we discussed there. Right? So machine automation. So. Technology selection and application. So is it something interesting for you?
Yeah.
Industrial automation, the main topic. Or you can work 2 or 3, maximum 3 together. Design a machine, and you can not only design, you can produce the machine, you can use sensors, PLC, you can program, you can learn lots of about the control, how you can control the machines, pneumatic, or I don't know, electric, electromechanic, motion control. Okay? Let's think about that before we come to this point. But this is not far away.
Next year.
Next semester, yes.
Sektörde olmayan bir şey mi böyle icat etmemiz gerekiyor diye.
Hayır, yani
Ya da olan bir şeyi de geliştiriyor.
something is, I'm here you see that to improve the quality for existing machine or machine part, or to improve the maintainability. There's also a problem regarding the maintenance. So maintenance. So the maintenance should be as quick as possible. Shouldn't take much time. Or the quality or safety, or to reduce cost, or to improve the quality, or to improve the performance. A second item. To check the how they produce. 4,000 per dollar. 24,000 or 30,000 in some cases, some bottles, and it is very interesting. You cannot follow by your eyes because it's just a red line turning. And this is today's problem. Okay, you have to learn how you can apply the technology and how you can apply your knowledge you learn, you gain during your studying time, and how can you apply this the correct way, or do you need something, for example. It shouldn't be a complicated system, simple, but you have to do on your own. Huh? You have to show, can work as a group, 2 or 3, not more than 3. And I'm for those type of graduation project, because the graduation project I faced here at the university, they are talking about something which is not. I know they have written from somewhere, and no calculation, no graph, nothing edited by himself. It doesn't help you. Huh? You should try to apply what you learned. And you see, you have to see, so, oh, this is really interesting. Huh? Now I'm starting to do something. Huh? So, okay.
Okay.
See you next week.
See you.
Thank you.
You are welcome. Bye bye.
Hocam tezler mesela bir firmanın bünyesinde staj yapıyorken de
Süper,
oluşturulabiliyor değil
süper
mi?
oldu. Süper oldu.
Yani onlar sana bir görev veriyor.
Var mı
mesela.
öyle bir firma?
Yok, ben bugün Mehmet Hoca ile konuştum da. Şunu geliştir diyor.
Evet.
Bunu nasıl daha iyi yapabiliriz diyor. Sen onu yapıyorsun. Yani test konunu onunla gibi bir şey.
Yani bildiğiniz, tanıdığınız veya staj yaptığınız veya yakınız bir firma varsa mesela şunu diyebilirsiniz. Neyi geliştirmek istiyorsunuz? Yani basit bir, yani sizin uğraşmak istemediğiniz ama sizin bir mühendislik problemi varsa 1-3-5 ay içerisinde çözülebilecek. Ben talibim.
Evet.
Şu otomasyon verin. Otomasyon da zaten günümüzün konusu yani.
Robot olacak.
Efendim?
Her şey robot
Yani
olunca.
evet, yani robot dediğimiz şey sadece işte dönen eksenli şeyleri anlamamak lazım. Robot dediğiniz kendi başına çalışan makineler yani. Evet. Hem robot, yani hem kendi başına çalışacak, hem de yaptığı bilgi olarak aktaracak ne yaptığını, gelen bilgileri de işleyip kullanabilecek. Artık yani iletişim becerisi gelişmiştir. Dijitalleşme diyoruz ya, dijital çağ. İletişim becerisi gelişmiş makine.
Evet.
Önce makine insan iletişimi, daha sonra da makineler arası iletişim.
Tam da bunlardan konuştuk.
Öyle
Yani
mi?
üretim teknikleri dersimizde
Ha.
Mehmet Hoca'yla. O da Endüstri 4.0 falan anlatıyordu da
Ha.
işte öğrenebilen makineler,
Evet.
birbirleriyle
information for the next step and so on. So it has different levels. So then you can say, okay, machines can deliver regarding productivity, regarding maintenance, or regarding any problem machine has. So then this information has to be processed by the department, or make some decision based on this information. Okay, later on you say the machines has to communicate each other, share the information. But I mean, the communication between the machines, we are far away. And I think in some cases, not in all applications, in some applications necessary, of course, regarding the safety, regarding the risk, for example. But we are talking about the machines we use in production line or assembly line. It's quite simple minds. I mean, the work they are doing. And it's a good point to start.
I have a question, like for the final year project, as you said, we need to decide, and like if we go for industrial automation.
Yes.
So basically what we need to do is like do innovation, right, in a machine. Like if there's some normal machine,
That's
we need to innovate.
to improve.
Yeah,
Any
improve.
improvement, yes. Any kind of improvement, like functionality, productivity means cycle time, for example. If the machine produces, let's say, 30 pieces in 1 minute, so you could maybe say not 30, 40, 50. For the same price. Okay.
Yeah, because right now I have a course, it's like technology management. And that also, like, basically we are learning the same thing, like how the innovation have been done, how the like computers have been outdated and laptop have been start being used more, and like how engineers and like companies are like making new innovations just to like keep on earning more money and like
Okay.
doing the, you know, what do we say, the competition.
Okay, competition.
Mhm.
Yes. So the machines are changing also, I mean, because of the competition. And today's, if you design a machine, if you want to design a machine, it's not only the functionality and the productivity, also safety is also very important. You know the C sign.
Yeah.
The C sign, I mean this one. If you want to sell your machine to the Europe,
European
C sign.
standards.
And C sign means this machine has to fulfill the directives, related directives of the machine, or the directives which is relevant for the machines. And to design and produce a machine according to the rules, it's not something easy. And that means, actually, you have a lesson also about the standard and C sign, directives and standards. Because the mechanical engineering or the engineering standard is nothing. Directives, I mean the machine directives and the standards, very important for you.
Lectures are only for like safety, health and safety, but not for standards.
It is also related to health and safety, and that's safety, especially safety for environment, health and safety for environment, for women, for others, animals, and so on. I mean, it is not something general. So we can talk many things about, I mean, environment or animals or any others. So regarding the, how can we protect the environment? But I mean, safety. So if you talk about the machine, you have to make risk analysis. So you have to make the risk analysis and see how big is the risk and how can you avoid the risk? How can you solve this problem? How can you create a solution which minimize the risk, for example. Solution into in the aspect of mechanical design or control system and so on, or selection of the products from the industry. And you don't produce each and every product you use in your machine. You have to buy from the other companies, from like sensors, and screws, and electric motors, and valves, and cylinders, and so on. Component to this. So considering the risk, by calculating the risk, you have to define the products you have to use in the machine and the risk factors of the product. So all of them are important. Therefore, the machine directives and standards, latest standard is also very important for you. Okay?
Tamamdır hocam.
That's
Sağ
enough
olun.
for today, huh?
Evet hocam. Teşekkür ederim.
Say bye bye.
And Professor, you have to submit this homework, the one you gave.
This is
Just give one question right now as a homework.
no, this is not homework.
No, not this. The other crank one.
Before the final exam.
Oh, okay, this one. We need to submit it like through mail or.
Yes, email.
Okay. And also, I wanted to ask, like, will you give another homework for machine design
No.
too? No.
No.
Or you will extend the deadline?
What is it?
The deadline for homework, machine design too.
No, next week we will discuss the project, but I will not give a homework.
Okay. How much is the weightage for project and
25.
Project is 25.
Midterm 25 and final 15.
Okay. Thank you
Okay.
so much.
You are welcome.
John, please, can you hear me? Hello, Professor, can you hear me? Hello?
I guess they have a bad connection. The internet in the university not good. That's why he disappeared, then he come back, something like this.
Okay, are you in the class or you joining lecture online?
They are doing it hybrid, like he is teaching from the university, and we are with him in the lecture.
In the lecture.
Yes, but
Okay.
and what was you was
Could,
asking
could,
about some?
could you please ask him? Because I actually sent an email to him. It's my first time joining this class. I always like come when the class is off or something. So could you please help me ask him when he's gonna hold the makeup meeting? Because I already sent an email, so I'm waiting for his email. I didn't get his email.
Bro, let me take your number and put you on a WhatsApp group. These things I have it in my phone.
Is he in the WhatsApp group?
No, the teacher no, but we are like there is a group of students. I guess they can help.
Okay, thank you. So I already joined
And
the group right now. I just joined the group.
you you
I
you
just
have.
joined the group right now. I just joined
Oh,
today.
okay.
All right, thank you very much, bro. I appreciate it.
No problem, bro.